Okay, we're going to wait a bit further. Okay, everyone just give me a second. I'm trying to connect my iPad, which was working very well until just a couple of days ago, but somehow it's not working for me. Let's see. Press on to open and then connect it up. Then, oh, what is going on here? Okay, let me retry. I'm sorry about this. Currently, I'm having issue with sharing my USB accessories disabled. Oh my God, what is this? USB accessories disabled? I'm sorry, everyone, just give me a second. Oh, okay, it's working. I don't know what happened there, but okay. Oh, all right, so that was close, but we are all ready to go. So as usual with the last week's lecture, if you have questions, please do type it on the Zoom chat so that I can look at them once a while and then trying to answer your questions, okay? And then my answer is going to be just, on the fly, so, but don't worry about it. I'll try to be as diligent as possible, trying to look at the chat window. So last week, what did we learn last week? We learned how to derive Bayesian linear regression. And it was a pretty, the heavy derivation we did. And then this week, we are going to do the very same thing. But before going into the details, we're going to just talk about one thing for now. And then what is the one thing is that we are now moving away from the supervised machine learning. So what we learned until now is called supervised machine learning, right? Where the supervised learning means that if we are trying to build a system that's going to learn to map from the input vector x, to some desired output y. And then the center box here was our machine, right? Now, this is relatively straightforward in a sense that someone or some algorithm was able to annotate the input, meaning that there is some kind of ground truth mapping going from the input to the output. All fine, that's good. And then all we need to do is try to come up with a machine learning algorithm that tries to mimic what that underlying algorithm is. Okay, that was fine. But now we're going into a case of unsupervised learning. And then unsupervised learning is very, very interesting in a sense that what we are given is just X. We don't really have a desired target there. What do I mean by not having any desired input? What we mean by not having any desired input is that we need to build a machine that is able to explain what is underlying this X. What does it mean to explain, right? That's a very difficult question. And then in this case, we often think about trying to make a machine that is going to generate X. And what do we mean by generate? So let's think about it in this way. So when is the case we tell ourselves that we understood certain mechanism? Often that is when we know how each instance of the problem was generated. So in the case of object recognition, one way to view this object recognition or the face recognition problem is to try to figure out what is the algorithm that's going to look at an image and then trying to simply detect what kind of person or who are in this picture. But the other way to look at it is that they're trying to think about what is the process by which this image was created or that this picture was created. Now, how does it happen? We start with a group of people in a scene, and then we know that that exists regardless of whether we have taken a picture or not. So there is a scenery, and then there are people in them. And then what we do is we're going to build a camera that is the optical acquisition device that's going to take a picture of the scene from a certain angle. And then based on what kind of, let's say, the photons were received by photoreceptor in this camera, we are going to get a specific type of an image or from a single angle. And then once we know how this picture was created, we can think about going back and then trying to reverse engineer how it was created. That is, we start from a picture and then we try to imagine how this picture was created. And then if our imagination was successful, then we can tell who are in this picture. So this is just an opposite direction of what we did with the supervised learning. In supervised learning, what we did was that given this input and an example output, that is desired output, we needed to try to get this machine that is able to learn to map from X to Y. But in unsupervised learning, our goal is to make a machine that is able to figure out what goes on underlying this X that gave a rise to this observation X. That is, if given an image, a picture, our machine should know that this picture was created by taking a two-dimensional image or the projection of the three-dimensional phenomena where there are objects that are arranged with respect to each other via a camera. And then once this machine is able to figure out the way in which this X was generated, then we can use that information in order to learn more about the data itself. And then that is the goal of this unsupervised learning. And then unsupervised learning, of course, drawing this kind of diagram is always fun. And then the diagrams are fun to look at, but we gotta go into a much more detail and then much more, let's say, foundational stuff in order to understand what is going on and then how we can do this kind of unsupervised learning. So in particular, the way in which we're going to approach this unsupervised learning, hold on, let me just the lines here, is called matrix factorization. So matrix factorization, as the name suggests, tries to factorize a given matrix into two different matrices or the product of two different matrices. But then we need to think about first what this matrix is, right? So what is this matrix? What we are going to do is we're going to build a matrix X to be, okay, I have to be careful because I always messes up between the column vectors and row vectors, but we're going to stick to the row column vectors now. So each vector could be thought of as a matrix with a single column. And then what we can do is now we can stack them next to each other or put them next to each other in order to build a matrix with multiple columns, right? So we have the n many data points as usual, which means that we have n many input vectors. So each and every one of these input vectors are d-dimensional, as we have learned already. And then these d-dimensional vectors are concatenated to form this large matrix X that is d by n. So this is the d dimension. So each row corresponds to each dimension of the input, and each column corresponds to each example that we get from our data set. So this is my X. And then what I want is to factorize this X matrix into product of two matrices, where those two matrices are W, which is going to be R d by d prime. So this is going to be my Wayne matrix. And then Z, which is going to be d prime by n. And then, of course, there are many different ways to call this matrix Z, but I'm going to call it code matrix. Let's think about this code matrix first. What does this code matrix look like? This code matrix actually looks very much like the input matrix. So I'm going to use the input matrix here. Input matrix X. What does that mean? So we have the same number of columns. So we have the n many columns in Z as well as in the input matrix. And then, but except that the rows, the number of the numbers of rows differ. So we can rewrite this Z matrix also similarly to the how we rewrote input matrix. Z1, Z2, and then Zn, where each of these vectors, these are column vectors, right, is the prime dimensional vectors. And then what it means is that for each X, so for each training instance X, we have a corresponding code vector Z that is of the different size. So the input vector was D dimension. And then now for that input vector, I have the corresponding code vector that is of D prime dimension. And then that is really important to know, right? What it means is that the goal here is to get a code vector of an input vector, D-dimensional input vector, where the size of this code may not correspond exactly to the size of the input. So given these three matrices, what are these three matrices? First one is the input matrix, second one is a weight matrix, and then the third one is a code matrix. Matrix factorization corresponds to a problem where we want to try to factor X into two matrices, or into the product of two matrices that are W and Z. So our goal is to find both, so it's important, we want to find both W, the weight matrix, and Z, the code vector matrix or the code matrix that explains the X as well as possible. So the product of this weight matrix and the code matrix should be as close as possible to this original input matrix X. And then what that means is that these product of these two matrices is going to explain X as well as possible. So this is what we meant by matrix factorization. And if you look at this equation, you notice, or that you must be reminded of something that we learned last week. That is a linear regression. In the case of linear regression, and then you also saw it the lab session last week, what did you see? In linear regression, the goal was to get Y starting from W. And then how do you get that? You're going to multiply X with the W. And then you're going to add some bias. And then our goal was that the difference between the X times, or W times X plus B and the Y. And then let's forget about the fact that we have the bias or not here, because bias can always be zero, right? How do we do that? In the case of the linear regression, we could have simply set bias to the average output. So we can actually ignore bias. Then we see a stark similarity here. So there is a product of two matrices here on the right side for both linear regression as well as the matrix factorization. And then there is a single matrix on the left-hand side for both Bayesian linear regression as well as matrix factorization. But then what is the difference? What is a major difference between these two is that in the case of linear regression, we observed both the left-hand side and the part of the right-hand side. On the other hand, with the matrix factorization, only thing that we observe is the left-hand side, which means that we have to figure out how we are going to divide the roles of how we are going to define or assign the roles to the weight and the code matrices ourselves, instead of relying on one of them being fixed to some value. So this is a very interesting problem, because one thing is that this problem is trivial. Why is it trivial? The trivial solution that I can give you is that I'm going to simply set the weight matrix to be identity. That is, W is going to be a diagonal matrix where the diagonal is simply all ones. And then I'm going to set D prime to be identical to D. So the size of the Wayne matrix is going to be D by D. So it's an actual identity matrix, square identity matrix. And then my code matrix Z is going to be set to be X. So my code is going to be identical to actual input or the observation X. Then this problem is perfectly solved. However, that really doesn't tell me anything about the actual input matrix or the input vectors. And then the goal of unsupervised learning, so goal of unsupervised learning is to figure out what goes on the line or what goes inside this input vector. Except that if you under that kind of trivial solution, we really don't see any of those. So what it means is that we must have certain type of constraint or the assumptions. That is, we must have, or we must impose a set of constraints on W and Z. Now, why is it constraints only on the W and Z? Is because X is given. So we do not touch X ourselves. So we must impose some kind of constraints on W and Z in order to find the interesting structures underlying the input data. And then this turned out to be one of the most interesting things you can do in any kind of machine learning. That is, in order to find something interesting from the data, you have to assume certain constraints or the structures behind the parameters or the machine that you're building. And in this case of the unsupervised learning as matrix factorization, we are going to look at several ways or the several different ways in which we can impose set of constraints on W and Z in order to uncover different underlying structures. Okay, so then what will be the very first thing that we are going to learn? The first variant of the matrix factorization that we're going to learn is principal component analysis. Or in short, we often call it PCA. And then this turned out to be one of the most important unsupervised learning technique that has ever been invented and has been used so far. And then even although it was invented or put forward by Fisher in early 20th century, like 1904 or something, it has not been faded away, but is being used even more and more every day. So what is the constraints here? So our constraint is actually pretty simple. Our constraint is that the code dimensions have to be decorrelated. So the constraint is that the code dimension have to be decorrelated. Now there are a number of terms that might not be too that you might not be too familiar with. So let's go over them one at a time. So what do we mean by the code dimensions? In this specific case, what we say is that we look at each Z. So we're going to look at a individual Z as a sample from some distribution over Z. I'm going to use Z. Z is used a bit too much, but you'll have to work with me. So it's going to be random variable. So we're going to assume that there is a distribution over these code vectors, that is some code random variable. And then these n many samples that we got, these are actual samples from this samples of this random variable Z following some distribution. I am not going to care too much about what is the specific distribution that is, but I can just assume that these ZNs are all coming from this distribution. And then when I say code dimension is, first, remember that this Zn, the A sample from this code distribution is D prime dimensional. What it means is that there's going to be Zn1, Zn2, all the way to Zn d prime. That is, there are d prime dimensions in this code vector or the code sample Zn, and then this code dimension correspond to one of these d prime many dimensions. And then now we need to think about what do we mean by decorrelated. Now, decorrelation has a very specific meaning in this kind of multivariate random variable. That is, if we look at the covariance of this z random variable under whatever the distribution that we decided to look at, then this decorrelation corresponds to this covariance matrix being a diagonal matrix. So the covariance matrix measures how similar or how each dimension, a pair of dimensions move together. So when the value of the first dimension goes up and then the value of the third dimension goes up together, then we're going to say the first and the third dimensions of this code vector or the code random variable are highly correlated. Now, of course, every dimension is perfectly correlated of its own, together with its own. However, when we say it's decorrelated, now we start thinking about all the off-diagonal terms, that is the pair of two distinct dimensions. And then when we look at two distinct dimensions, they should be decorrelated, meaning that it doesn't really matter whether one of them goes up or not, the other one goes up and or goes down independently from the other one. So what does that mean? So this kind of covariance matrix often is going to be d prime by d prime. So there are going to be d prime many rows, and then there are going to be d prime many columns. And then we can look at two different parts. So we're going to look at this entry that is I and j, where I and j are not not equal. And then there are going to be a diagonal entry that is where I and j are equal. And then if you look at this, one of the off diagonal entry, that is going to look at the correlation between ith and jth dimensions. And then the diagonal entries correspond to the variance of each dimension. And then hopefully you remember what the variance and the correlations are from the earlier probability and statistics course or the linear algebra course that you have taken. And then now there is one assumption that we are making. Our assumption is that the expectation of this z is going to be 0. That is, these z vectors are all standard. And then we have seen this kind of assumption earlier last week when we tried to derive the Bayesian regression. We assumed that the input vector x was standard. That is, we assumed in the Bayesian linear regression that this input vector x was standard. And then that's identical to having z standard. So in this case, we're going to assume that the z is standard, which is not really like the necessary, but this helps in deriving the whole principal component analysis. And then with this assumption, the covariance of z is going to be written as 1 over n, goes from n to 1, zn transpose. So where the 1 over n comes from the fact that we are estimating covariance using n many, we are estimating covariance empirically using n many samples from this sum distribution over z. And then for each example code or the code vector zn times the zn transpose gives us an empirical estimate of this covariance matrix. And then what we want is that the constraints that we put is that this covariance matrix or the estimate of the covariance matrix of the code vector is diagonal. And then of course, we said just diagonal. What it means is that we can in fact ignore for now this 1 over n factor, right? Can be ignored. Why is that? If the covariance matrix of Z is diagonal, then the same thing multiplied with n is also going to be diagonal, because we haven't really put any kind of constraints on what the values of this diagonal should be. Only thing that we have put constraint on is that all these off diagonal components need to be 0. So that is the constraint. And then now, how are we going to get to this code vector, code matrix, and the weight matrix starting from X, that is the observation matrix, in order to satisfy this constraint? How we are going to do it is we're going to start from the covariance matrix of the input X, input matrix X. So let's go back to the input matrix. So our input matrix was, a matrix that is D by N, where the D is the dimension of each input vector, and then N is the number of N's. So there's a question on the Zoom chat by Wen. Should it be cov Zn before the assumption? No, so the Z here, no, that's not true. This should be Z. So Z is this random variable Z. This random variable corresponds to the code vectors. And then our code vectors, actual code vectors, so we have n many of them. These code vectors are samples from this random variable Z following a distribution. And then what we do is that we don't really care about the actual distribution, but we want this covariance of this Z, that is a random variable, not the individual sample, to be diagonal. So that's why this is not the covariance of the Zn. Zn is not random variable anymore because there is already a sample from the random variable Z. So there is no such thing as covariance. What we are looking at is the covariance of the random variable Z. And then how we are going to estimate this covariance of random variable Z is by using these n many samples from this random variable Z, following some distribution. We don't really know who they are, but we know we have access to these random variables. And then how we do that is that assuming that they are all centered, we look at their outer product and then the average of those outer products. So that's how we do that. So now we look at the input matrix, and then we're going to again assume, so we're going to make another assumption that expectation of this X, so the X here is a random variable, right? Why is it a random variable? Any nth input variable, input vector n is again a sample from random variable X. So we are looking at two random variables here. So the random variable Z over Z and the random variable over X. And then what we are trying to assume here is that the expectation or the expected value of this random variable X is 0. And then this assumption is very, very easy to satisfy. So how do we satisfy it? We simply center our observations ourselves. And then that can be done in advance as a pre-processing step of the data. So we're going to simply say that, okay, we assume that for now. And then now we can compute the covariance of X as well. And then this covariance is 1 over n, n1 to n, and then, oops, not C, but in this case, xn and xn transpose. As usual, nothing has really changed it. But then what we want is that because as I said, we said that this kind of scalar scaling doesn't really matter in the case of looking only at the covariance and then trying to change the covariance to be diagonal. So we're going to look at a so-called scaled covariance, which is going to be simply multiplying this covariance of the X. So we have the covariance of X with n so that we end up with only the summation. And then in fact, this summation or the sum of all these outer products of the xn's can be rewritten as a large X times a large X transpose, where this X is going to be input matrix. I understand that it's very, very confusing because the similarly looking letters are used for the different purposes, but it's kind of, let's say, even more confusing if we start introducing all these new variables. So we're going to stick to this kind of notation. But as you get used to it, you're going to see immediately whether, based on the context in which they appear, you're going to see whether they are referring to matrices, vectors, scalars, or the constants, or random variables. Now, so we look at this covariance matrix or the scaled covariance matrix of this variable x. Okay, let me see. There is one question from Marina on Zoom chat. Could you repeat why we can ignore 1 over n in the covariance of Z? So we are not ignoring 1 over n. So 1 over n here, 1 over n in the when we're trying to estimate the covariance of Z. However, we can ignore 1 of n when our constraints is all about whether this covariance of Z is diagonal or not. So all we are trying to do is that the covariance of Z is diagonal, and then you take any diagonal matrix, multiply with any scalar, it's still a diagonal matrix. That's why we can actually ignore it for our purpose of imposing the constraints. And there's another question from John. So the input as an input matrix is different from X inside Colvex. That's precisely true. So X here, this is the input matrix. And then this matrix has a D many rows and then N many columns. Now this X is a random variable X, which is used inside the expectation. And then this one is only D-dimensional random variable. So it's a multivariate random variable. So those two are different. So once we start looking at this scaled covariance of the X, then PCA could be thought of as decorrelating this scaled matrix. That is, PCA aims at decorrelating this decorrelating X. That is, in this case, the random variable X. Okay, now what it means is that if I write it down again, so we start with some scaled covariance of the X, and then this covariance of the X can be, this scaled covariance can be estimated using the input matrix as the product of X and its transpose X. And then it ends up being D by D matrix. And then what we want is that my PCA is going to turn it around so that it's going to be some kind of, so that this is going to be some kind of diagonal matrix. So we start with the input matrix that tells me about where all these input vectors are. And then now what I want is that I want my PCA to make them transformed in a way that the transformed data points, the covariance of the transformed data points or the code vectors is diagonal. So that is the goal of PCA. And then here, if you notice, actually from earlier on, you must feel something looks really, really similar, some kind of deja vu here, right? What is this term? This looks really, really similar to the CXX from last week. So last week we learned about the Bayesian regression. And one thing that was showing up over and over last week was this CXX term, or the C times the C transpose. Of course, back then there was a plus identity. But in this case, we're going to just look at X times the X transpose without identity added here. And then the CXX showed up over and over. And then if you remember, we talked about how CXX tells us about how the data is distributed. So data might be distributed far along one axis, far along another axis. And then this CXX, of course, shows up here. Not because it's talking about how the data is distributed, but because that's how the data is distributed is measured using this covariance. So what does it mean for how the data is distributed? Is that the data is distributed along certain dimension a lot and a lot if they move together. If things don't move together, then we can say that, okay, data cannot be too far away off the axis. Right? It's kind of confusing, but you're going to get it soon. But let's follow along the derivation of PCA, but let's remember this existence of CXX here. Now, then our goal here is to try to decompose this CXX into a form that allows us to transform this X, the input matrix, so that the covariance is going to be diagonal. And then the tool that we use is so-called Eigen Decomposition. Hopefully you immediately are reminded of yourself about the Eigen decomposition or eigenvalues, but it's okay. We're going to go through it ourselves, here together. So in the Eigen decomposition, we're going to take this CXX matrix, that is a square matrix because it's the D by D matrix, into a product of the W transpose, sigma, and W. So these W's are essentially the weight matrices. We're going to see how they are weight matrices. And then this sigma is going to be a diagonal matrix. And then in this eigen decomposition, more specifically, W consists of eigenvectors. And then sigma is a diagonal matrix of eigenvalues. So the eigenvectors and eigenvalues, and then we use the identity that any square matrix can be decomposed into the eigenvector matrix transpose times the diagonal matrix of eigenvalues times the eigenvectors. So where does this eigen decomposition comes from? It comes from the definition of eigenvalues and eigenvectors. So what was the definition of the eigenvalue and eigenvectors? Now, given this CXX, let me see if I did everything correctly. Now, yeah, given this CXX, one eigenvalue, so we're going to eigenvector, so we're going to look at the ith eigenvector. So WI, if I multiply CXX with the WI, then what I end up with is, let me see, I have to be a bit careful about writing things here. What I'm going to get is the ith eigenvalue times the ith eigenvector transpose here. Do I need the transpose because it's going to be d by 1? Oops, I'm sorry. This should be not the transpose, but the transpose. I have to be a bit careful. Yep, okay. All this transpose business is a bit confusing always, but let's say Wi, so it's going to be d by 1, and then this is going to be, so this is the d by 1, and then d by d, resulting in d by 1, and then this is d by 1, so this is fine. Okay, so we have the CXX times Wi, the ith eigenvector, should be the lambda I, that is the ith eigenvalue, times the eigenvector itself. And then this is how the eigenvalues and eigenvectors are defined. What it means is that we get the eigenvalues and eigenvectors by solving this so-called characteristic equation. And then now, given this, we can think about rewriting or the stacking all these for different i's, I going from 1 all the way up to d. What it means is that if I stack it up, then I have CII, and then I'm going to have WI, oops, not W1, W1, and then I'm going to just set them one at a time, right? So this was the D, so here WI has a D many rows and then one column, so I'm going to put them next to each other. WD, there are going to be up to D many eigenvectors. And then what I end up with is, here I'm going to have lambda 1, lambda 2, all the way to lambda d. And then all the off diagonal entries are going to be all zeros. I need to actually move this around a bit. And then I'm going to put here In this case, W1 transpose, W2 transpose, all the way to WD transpose. So this is just, trying to stack them, right? So by stacking, CXX times W1 equals lambda 1 W1, CXX times W2 equals lambda 2 W2, CXX times W3 equals lambda 3 W3, and then so on all the way to CXX times WD equals lambda D times WD. We get just this one simple equation that consists of CXX as usual, and then a matrix of the eigenvectors, and then the transpose of the matrix of the eigenvectors, and then all these eigenvalues. So it's a diagonal matrix with eigenvalues. So far, so good, right? So now we write it like this, and then we're going to assume here that we know how to get all these eigenvalues and eigenvectors. And then that can be done with the many different algorithms. And then one of the algorithms would be power iteration, but power iteration is not necessarily good when you want to estimate all these eigenvalues. But I'm going to assume that you have learned how to estimate all these eigenvalues and vectors from the linear algebra course, which is one of the prerequisites. And then now let's see. What was our W? W was defined as a matrix of the eigenvectors. So what we are going to say is, let me see, I'm going to use this to mark this here, is that the W is going to be a matrix where we have eigenvectors stacked next to each other. So this matrix here is going to be large W. And then that was our range matrix. And then now let's do some rewrite of the things. So this is going to be W transpose. What it means is that, and then these W's are orthonormal matrices. Why are they orthonormal? That's because of the definition of the eigenvectors. So when we extract all these eigenvectors, we can get as many eigenvectors as there are rows of the columns in this original square matrix. And then all those eigenvectors are orthonormal, meaning that the dot product between any pair of eigenvectors that are not of the same eigenvectors is going to be 0. And then if you compute the dot product of any eigenvector with itself, it's going to be 1. So that is what we mean by the eigenvectors are orthonormal. So I'm going to write here that the eigenvectors are orthonormal. Although we can just make a version with the orthogonal as well, but we're going to stick to the orthonormal version. And then what it means is that this W is a orthogonal matrix. So W is an orthogonal matrix and also the orthonormal matrix. It's essentially the same thing, except for that each vector could be scaled or not. And then in this case, a very interesting property is that the W transpose W equals W times W transpose, and both of them are equal to the identity function. So this is the amazing property of that. What it means is that we can now rewrite this above thing, which can be rewritten as the CXX times W equals W transpose times, I'm going to use sigma as a shorthand notation of this diagonal matrix with the eigenvalues, into either CXX equals W transpose sigma times W. So how did we get here? Is that the CXX W times W transpose equals W transpose times sigma times W I actually should have done something more careful. Let me see. I think my transpose is somewhere wrong. Let me see. Let me see. I use the transpose here so that I should get the transpose here as well. Oh my, I'm sorry about this. We'll have to rewrite this part. This is my bad. This is what happens when you are being a bit sloppy about the dimensions in this linear algebra. So here we're going to do the very same thing as on the right-hand side. So what I mean is that I'm going to do transpose, W2 transpose, all the way to WD transpose. And then, in fact, everything still works as usual. I'll just have to move things around a bit. Okay. And then what we get is, here is the W transpose as CXX times W transpose equals W transpose times sigma. So what we do is, we're going to multiply that with the W from the right, and then we do that both sides. And then what we notice here is that this part, W transpose times W, is identity. That actually leads us to this equation that is CXX equals W transpose times sigma times W. Now, so this is how we get the eigen decomposition. So why is this eigen decomposition any interesting? Because another way to look at it is that we're going to multiply the whole thing from the left and right by the W and W transpose. And then now you already see where I'm getting it, right? So how did it happen? Is because W times CXX times W transpose equals W times W transpose sigma times W transpose. And then we again notice that we have W times W transpose on both sides of this sigma. And then these both terms are going to be simply the identity matrix. And then identity matrix is just like 1 in a scalar multiplication. You can simply ignore them. And then what we see is that if we start from the covariance or the scaled covariance of the input random variable x, and then if we multiply these both sides, so both sides, by this eigenmatrix W and W transpose, then what we end up with is this sigma that is a diagonal matrix with the eigenvalues. So let's go back all the way up and then trying to see what was the goal of this PCA. The goal of this PCA was to decorrelate the input vector x. That is, we want our PCA to be able to transform or change the x, the input vectors, in a way that this scaled covariance, that is the product of the input matrix x and its transpose, becomes a diagonal matrix. And then what we see here is that we have this scaled covariance, the CXX, and then by multiplying the left side and the right side by W, that is the eigenmatrix, and its transpose, we were able to turn this scaled covariance into a diagonal covariance, where the diagonal terms correspond to the eigenvalues. Now, this is really interesting. Now, let's continue to rewrite it a bit. So this is really interesting in a sense that this, in fact, solves the problem of diagonalization of the input covariance, the input scaled covariance matrix into this diagonal covariance. And then if we continue to rewrite it further, then what we see is that it's going to be W x transpose W transpose equals sigma. And then this term, let's just rewrite it further. This term is going to be Wx times Wx transpose. This just comes from the one of the identities associated with the transpose. If you have a product of many matrices, and then if you want to look at the transpose of it, then what you do is you look at the transpose of all those matrices involved in this product, and then multiply them all together, however, in the order that is opposite, in the reverse order. And then this equals sigma. And then now the interesting thing comes in is that the W times X is, let's hope that I wrote the correct thing here. No, I didn't write it in a correct way. Okay, so I'll just put all the transpose here. It's going to be D prime by D. So I just added the transpose here to make everything work well. I'm sorry about that. This is always so confusing. Too many the variables and dimensions. And then what I see is that the Wx is in fact Z if and when W is an orthonormal or the orthogonal matrix. Why is that? Because we can write this Wx equals Z. We can see that it's equivalent to X equals W transpose Z if W is orthogonal matrix, orthogonal matrix. And then in our case, because W is an eigenmatrix, this condition holds automatically. And then thereby this condition also holds. And then in this case, what we get is we get a Z. And then, okay, instead of writing it like this, if I write it down as Z times Z transpose, and then we go back up, and then if you remember how we define the covariance of this Z, that was the sum of the outer products of the code vectors, and then this is in fact identical to 1 over n Z, the code matrix, times its transpose. So here, let's see, this Z, oops. So Z times Z transpose, and then we talked about how 1 over n can be ignored because all we want is this covariance to be a diagonal matrix. And then if Z times Z transpose, so Z times Z transpose is diagonal, then however we multiply this matrix with the 1 over Z, covariance matrix is also going to be diagonal. And then we come down all the way, and then what we notice is that we do have the Z times Z transpose here. And then that is just sigma, which is a diagonal matrix. So what does it tell us? What it tells us is that this eigen matrix W, so eigen matrix W of this scaled covariance matrix CXX is the correct way to find W. And then the Z, the code matrix, is going to be obtained by simply multiplying the input matrix from left with this Wayne matrix. And then once we do that, this code matrix has a diagonal covariance matrix, which was the constraint that we wanted to impose. So let's write this procedure once more. So first, Eigen decomposition of the scaled covariance matrix of the input X, which is associated, computed by going through each and every example. So going from N1 to N, and then we look at the outer product, which is identical to computing the X times its transpose, where the X is going to be input matrix. And then we do the eigen decomposition of this CXX. And then what we end up with is the W matrix. And then this W matrix is an eigen matrix where it has all those eigenvectors. WD. So this is going to be eigen matrix, eigenvector matrix. Be more specific, matrix. And then as part of this eigen decomposition, we get a sigma as well, which is going to be a diagonal matrix with the eigenvalues. All zero, and then these are eigenvalue matrix. And then by doing so, we already got our Wayne matrix. So this is identical to the Wayne matrix that we wanted to find. The reason why it's identical to what we want is that because this eigen matrix turned out to get us a code vector. So we can now obtain the code vector by multiplying this X with the W. And then interesting thing is that this leads to the covariance of Z being diagonal. And then this diagonal, what is this diagonal? It's a sigma here. So we get the code vector by multiplying the input matrix with the eigenvector matrix or the Wayne matrix, and then we get Z. And in this case, this is exact. Thereby, what we end up with is that we know that this process solves the problem of estimating X as a decomposition or the product of the W transpose and then Z, the code matrix. So before we move on, there is a question from Carol. So we can't determine the D prime. It depends on the number of eigenvectors. Yes, so this is a really interesting question. Is that so how do we know the D prime? So entire process so far has assumed that the D prime is identical to D and that this covariance matrix of the X or the scaled covariance matrix of X is a full rank. So those are the two assumptions. Once we have a full rank covariance matrix or the square matrix, then we can get as many eigenvectors there are rows or the columns in this squared matrix. So that's what we have assumed. So we have assumed that we can get up to D many eigenvectors. And then given that eigenvectors and D many eigenvectors and values, we get a code vectors that are again D dimensional. What it means is that all we do in this particular case is to take the input and then rotate it and then rotate and scale it. So linearly transform this into a code vector. And then this linear transformation is done in a way that the covariance or the scaled covariance of this code vector or the code random variable is going to be diagonal. Now, then that actually raises a big question is that does D prime have to be D? So let's try to answer the question. In order to answer this question, we need to actually think about one thing. So going all the way back to the matrix factorization, what we talked about is that our goal is to find the product of this transpose of Wayne matrix and the code vector so that it's going to estimate this X as closely as possible. Now with the PCA, if we set D prime to be D, so D prime to be D, what we end up with is a solution that solves this problem of matrix factorization exactly. Assuming that the covariance of the X is full rank, that is, it is invariable, then we can solve this problem exactly by solving this Eigen decomposition of the covariance of an X. However, often that's not what we want. What we often want is to use this kind of unsupervised learning or the matrix factorization to get some kind of compact code that is more compression of the input by throwing away the irrelevant details and then leaving only the important details from the data or the inputs. So what it means is that in the case of principal component analysis, we want in PCA, we often want D prime to be significantly smaller than D. For instance, we may want to set the D prime to be just 2, which allows us to get code vectors where each code vector consists of only 2 values. And then when we have only 2 values or the 2-dimensional vectors, we can simply plot them and then see how the data is distributed. So that's what we want to do. Then the question is, okay, we want to do this, and then we have all these eigenvectors and values. There are as many as D. Then the question here is that how do we choose a subset of these eigenvectors and values in order to get D prime to be small? That is, how do we choose a subset of eigenvectors and values in order to now minimize W and Z, where the X minus W transpose Z in terms of the Frobenius norm is minimized. So this is what we want to minimize. So instead of viewing this matrix factorization as a way to factorize a matrix into a product of 2 matrices, another way to write it down is to, just like what we have done so far, by writing down the cost function and then trying to minimize this cost function with respect to the parameters of our machine. So we have this PCA machine, and our PCA machine is fully characterized by the code matrix and the weight matrix, with the constraint that the covariance of this code random variable is diagonal. So, and then we were still solving this problem. So all we need to do is we know how to get the code vectors and the code matrix and the weight matrix to satisfy these constraints of the diagonal covariance of the code random variable. All we need to do is now we need to select a subset of those eigenvalues and vectors so as to minimize this Frobenius norm of the difference between the input matrix and the product of the weight and the code matrix. Now, how will we do that? So it turned out that it's actually relatively straightforward to do it. And then even there is an intuitive answer to that. However, we're going to just write down a very simple couple of equations that gives us the idea of what we should do. So what we want to look at is that this can be thought of as a reconstruction error, right? So that is, what we want is that our machine, okay, let's go all the way up. We want our machine, PCA machine, to generate this X. But then where this PCA machine generate this X from is from the corresponding code vector. So in a sense that starting from our code vector, our PCA machine is going to reconstruct the corresponding input vector. And then this cost function tells us about what is the difference, that is the error in this reconstruction. And then we can now write down the reconstruction error using only D prime component, where the D prime is going to be smaller than D, as sum of the I going from 1 to D, and then ZIN WI minus J going from 1 to D prime. D prime is the number of the dimensions of the code vectors that we want. So that's going to be smaller than D. ZJN times WJ and square. So if you look at this term, what we are looking at currently is just a one input. So we're looking at the reconstruction error of xn. So only the nth input. Why is it enough? Because this Frobenius norm that we get here is going to be the sum of the reconstruction errors of each and every input variable. So all we need to look at is just look at one of them and then see what happens. And then remember that the D prime is smaller than D. And then what we have done is to sort after sorting. Wait, no need for sorting. I'm sorry about that. Sorting the eigen is necessary actually. Vectors and values according to the eigenvalues. So I don't think this is actually necessary. Oh, in fact, this is not necessary. Okay, sorry about that. It's always confusing when I try to do all this derivation from scratch again. I did it several times when I was in my undergrad and my PhD program, but you know. So, okay, so we start from this, and then what we notice is that because the terms are shared, right? So we go from here 1 to D prime, which is smaller than D, and then we look at the product of the code vector, associated dimension of the code vector times the associated eigenvalue. And then we do the same thing here, but here going from 1 all the way to D that is larger than D prime. And then we do the same thing. What it means is that the terms that goes from 1 to D prime are going to all cancel out, however you sorted them, right? What it means is we're going to end up with computing the remainder of the size of the remaining dimensions. Oops, not D, but W, WJ squared. Because there is a shared part that goes from 1 to D prime, where D prime is smaller than D. All we now care about is going from D prime plus 1, actually, plus 1 all the way to D. So we are looking at the norm of the eigenvectors that goes from the D plus 1 dimension all the way to D in the code vector dimension. And then they're going to be all weighted by the actual value in the code. Oops, what just happened? Makes sense so far, right? And then the interesting thing you notice is that hey, hold on, what is going on here? Now I want to, what just means is that we are just removing all the parts that were overlapping between the first summation and the second summation. Okay, so far so good. And then the interesting thing happens. This one can be rewritten as going from J, D prime plus 1 to D, Z, so the Jth dimensions code vector squared times the norm of the Jth eigenvector. Now what happens here? The reason why we can actually remove all these cross terms, because this is a squared of the many summations, then what you see is that you get the square of each of the terms in this summation, but also you always end up with all those cross terms, right? So the product of the different terms. However, because the eigenvectors are orthonormal, meaning that the two different eigenvalues, when they are multiplied, become 0, we can actually ignore all those cross terms as they are all going to be 0. That is because Wi transpose Wj is 0 for all I that is not j. So that's why all the cross terms disappeared, and then the square term of each of the term in this summation, it can be written down as the square of the scalar. So remember, this Zj is scalar. So if we trying to compute the norm of the scalar times a matrix, you can write it down as the norm of the vector times the square of the scalar. And then we have the norm, L2 norm of this Wj. But if you remember, this term is just 1 because Wj's are orthonormal because of this normality here. So this is just 1, and then what we end up with is that this is going to be j d prime plus 1 d j squared. So this is the reconstruction error we get from principal component analysis. Now, what does that mean? Is that we know exactly what our reconstruction error is going to be by looking at the norm or the magnitude of the eigenvalues. And then what we want is that if we want this reconstruction error to be minimized, meaning that if we want this the sum of the squared eigenvalues, so there is a zj. Wait, hold on. Oh no, I'm sorry. So I'm actually going a bit too quickly. So what is this term? This in fact is a sum j going from d prime 1 to d, and then of the eigenvalues. So why is it eigenvalues? What were these eigenvalues in the diagonal? That diagonal was the variance. So diagonal consists of the variance of each dimension of the code because of this. The covariance of Z is this sigma matrix that is a diagonal that consists of all these eigenvalues. What this means is that because the Z is centered, this Zj squared computes the jth eigenvalue, meaning that the reconstruction error is proportional to the sum of the eigenvalues that were left out. So that is left out, right? Because we are looking only at the D prime, and then this reconstruction error is the sum of the eigenvalues of the left out portion. And then in order to minimize this, what do? We are going to simply sort all the eigenvectors according to the eigenvalues, the magnitude of the eigenvalues in a descending order, and then pick the top eigenvalues and the vectors. So what this implies is that we need to pick for PCA to minimize this reconstruction error, top K, oops, I'm sorry, not K, but D prime, top D prime eigen vectors and values. Because once we do that, whatever is remaining is going to be minimized. And then the minimization corresponds to minimizing this reconstruction error as well. So that's why in PCA, the process, in fact, involves a third one. First, we solve the Eigen decomposition of this covariance matrix, or the scaled covariance matrix, and then we obtain code vector using this Wayne matrix that we have obtained. But then what we don't want is to use all of this, but use only the top D prime eigenvectors, where the top D prime is determined based on how large the associated eigenvalues are. So this is how we end up with the principal component analysis. And then this is how we are going to get the principal component analysis with D prime, the size of the code vector, smaller than the size of the input vector. So this is one very particular example of the principal component analysis, and then you're going to learn how to, in fact, use this principal component analysis in the Wednesday's lab session. But before we finish, we have 4 minutes. Oh, Katrina is going to not like me because I'm not going to be able to talk about this too much. Let's think about just a second possible case of the matrix factorization. Because we already know that what matrix factorization solves can be thought of as solving this problem. That is the finding W and Z, so the Wayne matrix and code matrix that minimizes reconstruction error with some constraints on W and Z. We can think about many different ways to solve this problem or find the variant. And then before we go continue, let's just answer one question from Liam. Is PCA kind of the opposite of radial basis function in that we want to reduce dimensions instead of increase them? Yes, so the radial basis function network there, we wanted to increase the dimensionality, but then the increasing the dimensionality was to solve the problems that are not linearly separable. In the case of matrix factorization, we do not have such a notion as the linear separability or anything. There is no problem to solve here. Our problem is to find some regularities underlying data. And then PCA often is focused on finding a few principal components of the axis that explain the data most by minimizing this reconstruction error. So in some sense, yes, they are related, but in other sense, or the major sense that we are working with, no, they are not necessarily related to each other. So now, what would be the other type of the constraint we can think of? One constraint that turned out to be extremely powerful is so-called non-negative matrix factorization. And then often in short, we call them NMF. And then in NMF, the constraints that we put are W, all the elements of W is greater than or equal to 0. And all the elements in code matrix also greater than or equal to 0. And then what this implies is that what this automatically implies is that the input matrix, input should be non-negative as well. Because if the Wayne matrix and code matrices, both of them are non-negative, their product has to be non-negative as well. And then if our input is actually, an input contains a lot of negative entries, it doesn't make any sense to do non-negative matrix factorization. However, this non-negative matrix factorization, these constraints turned out to be extremely powerful notion. The reason why it's powerful is that our data, one big assumption that we often make about our observation is that our observation is a sum of many different underlying fundamental building blocks. What does that mean? Let's go back to the original example of the object detection. So we assume that the objects are placed in a scene, and then we have a camera that's going to take the 2D projection of this 3D scene. And then what we want to do is that if we want to know which objects are there, and if you think about it, you can start by reconstructing the whole image by starting from the scene alone. And then we're going to add one object at a time. And then of course, there will be a lot of occlusions and there may be interference, but in the very basic setup that we can imagine, there is no such thing. All we do is that on the top right corner, we're going to put one object, let's say a bird. On the top left corner, we're going to put sun as an object, then another object, and another object. And then in fact, you can think of this matrix factorization as trying to figure out which object appears in this input X. And then the type of the object is measured or captured by this code matrix Z. So each dimension in Z may correspond to which object appears to which degree, and then associated weight vector, that is the eigenvector in the case of the PCA, tells us about what that object looks like. You're going to see precisely what I meant by on Wednesday, and also throughout the rest of the semester, by what I mean by this kind of object-centric representation. And then this non-negative matrix factorization, this non-negativity turned out to be an excellent way to say that our underlying assumption is this additivity of different objects on the image. And then how we can solve this problem turned out to be a bit more involved, but the whole thing, in fact, applies identical here from the supervised learning. You compute the gradient of this cost function with respect to both the Wayne matrix and the code matrix. Now, of course, if we use the gradient and then update the Wayne matrix and code matrix without any thinking or without considering these constraints, then it's possible that the resulting Wayne matrix and the code matrices may contain negative values, and then that's not what we want. So one easy way to go about is to use the projective gradient descent algorithm that you're going to see on Wednesday how it works. That is, we're going to simply eliminate all those negative components by setting them to either 0 or a very small random number. And then that actually gets us so-called non-negative matrix factorization, which is one of the most useful matrix factorization or unsupervised learning algorithm for text analysis, as well as even the biological sequence analysis. So before we wrap up today's lecture, there are 2 questions that I'm going to try to answer quickly, and then we're going to finish it. So Chris asked a question, whether there is any difference in implementing PCA using SPD instead of eigenvalue decomposition. It is definitely possible to use the singular vector decomposition instead of eigenvalue decomposition, where the singular value decomposition is going to decompose the input matrix X directly rather than its scaled covariance matrix, as we showed with the eigenvalue decomposition. And then that's often more desired because it's computationally better. You're going to see how these things are implemented in PCA, underline this scikit-learn in your homework and so on. But yes, in practice, singular value decomposition is used much more widely, and then you should actually stay away from using the eigenvalue decomposition. However, for the exposition purpose, eigenvalue decomposition gives you the better idea of what this PCA does. And then the last question that I'm going to answer is from Carol on what the F means in the cost formula. Oh, yes. Okay. So the F here, let me use the F here, says that this is the Frobenius norm. So what is the Frobenius norm of a matrix? What we do is that it's an analog to the Euclidean norm of a vector. In the Euclidean norm of the vector, what you do is that you take each element from the vector and then square them and you sum them. In the squared Frobenius norm of a matrix, we do the exactly same thing, except that it's not a vector. So we look at the entire matrix, we take each and every element, square them, and then sum everything. And then that's going to be the Frobenius norm of a matrix. So that actually concludes our lecture today. We are going to have the lab session on Wednesday, and then please do attend using Zoom. Today's lecture has also been recorded. I'm going to upload it on NYU stream as usual, and then I'm going to post it on the campus wire so that you can review it if you want in the future. All right, and that's it. Thanks for attending the Zoom-based lecture.